Hoessbacher from Marvell. And it's a pleasure to introduce her here and looking forward to her perspective on CPO.
Thank you, David. Thank you, Optica, for the kind invitation. You should be able to see my screen.
We can see it.
Very good. Thank you so much. Modulating the AI era. This is a modulator talk because this is my background. So this is a technology talk too. Let me just find my pointer. Less system level, more component level. And if you look at the material platforms on a high level, there's silicon photonics, indium phosphide, and lithium niobate. And this is a very simplistic view, but we all want bandwidth density and bandwidth speed, but we also need to look at the manufacturability and the complexity. And this is where silicon photonics is great because it leverages mature CMOS processors, so it's highly scalable, but it has some challenges in terms of speed if you compare with the other technology platforms. I also wanted to give you a chance to look at some notable papers, so please feel free to look this up, but I really want to focus on silicon photonics because this is what most folks consider for CPO. Now, if you look at silicon photonics modulators, again, this is never complete. There's Mach-Zehnder modulators, microring modulators, the germanium silicon electroabsorption modulators, and then there's ways to integrate lithium niobate, for example, via microtransfer printing and other techniques. So going from the right, microtransfer printing is a really interesting technology that I think we should follow. It has a good speed, as far as I know. We still have challenges in terms of yield. It's a relatively new technology, so we have to look at this. And in my perspective, also the size of these modulators are not yet convincing. Then there is the electroabsorption modulators, great speed, great size, complexity. I would say it's moderate because we don't know yet what it means for the system, right? These are mostly in the C-band, so we need to think of whether we can live with it, and maybe we can. And then the microring modulators, if you have been at OC, these have received a lot of attention. I think almost all of the modulator talks were on microring modulators. And this is because of the great bandwidth density that we can get with those. In order to get the bandwidth, we really need to play all the tricks. So we need resonant peaking and equalization to get there, but it's doable. And also we need quite some thermal control and very reliable processes. So to get these dimensions, it's not easy, but folks are working on it, and there's been great progress made. So that's why, as a community, we would still like to use the Mach-Zehnder modulators because they are kind of easier, but they are limited in terms of modulation efficiency. So they are not so good in speed and not so good in size. But if we can make that work, this would be our dream. So what if we had silicon photonic modulators that were much smaller and much faster? So the typical length of a silicon photonic phase modulator is a few millimeters. What if we could go down to the micrometer scale? So if you can't see this dot, that's the whole point. It would be significantly smaller. And likewise, what if we would not be limited to 60 gigahertz, but we could go to the terahertz regime? But there's a problem with that, and that's physics. And I'm showing this monument here from Ernst Abbe. Ernst Abbe was the one who discovered the diffraction limit of light, and this is set in stone, right? So if we think about how much we can focus light, this is always limited by the wavelength of light. So the dimensions will always be limited by this lambda. And this is why photonics devices are really, really big and wafer area is expensive. So what can we do? Well, we can use a different physical effect. And this is where plasmonics comes in. And plasmonics is utilizing so-called surface plasmon polaritons. And simply speaking, this is just the solution to Maxwell's equation at a metal dielectric interface. So these are surface waves that are propagating along this interface. They're interface bound. The optical confinement is below the diffraction limit. And it's also a very lossy propagation. So if you want to utilize those, you need to really make the micrometer small, otherwise you will be killed by the losses. So let's have a look at how we can use this effect to build devices. And we typically use metal insulator metal MIM slot waveguides. So this is how it looks like. The typical dimensions are well below the operating wavelength at 1550 or 1310. We fill this slot with a pockets material. So here it's an organic electro-optic material. And then you can look at the optical field, which is highly confined to this slot area. So this is where the wave is propagating along the slot. And then if we apply a voltage across these metal plates, because of the pockets material, this organic electro-optic material, there's a refractive index modulation in the plasmonic slot waveguide. And what you can also see is that there's a very good overlap between the optical field here and the driving electrical field. So you almost see no difference. And this is also not the case with other modulator schemes where you would have a huge difference, and then obviously you also lose part of the field that cannot be utilized. So it's a very efficient integration. However, as mentioned, it's lossy. So we would only use it where we really need it. So for the active components, we keep all the routing, the coupling, the splitting, and the interfaces in normal silicon. So for all those that have been working in silicon photonics, we'll not take that from you. We just add this component where we need it. So if you look at some real dimensions, on the top you see a thin film lithium niobate IQ modulator. So this die is 50 millimeter long, and the IQ modulator section 7.5 millimeter. Compare that to a plasmonic IQ modulator. So this is significantly smaller. And again, you cannot even see the active section in this picture because it's so small. And because it's small, it also means it's really, really fast, because ultimately the slots that I've shown to you are capacitors, right? And if you have small capacitances, it also means you have small RC time constants, or at least the C is small. And also the R, the resistance, is small because the metals of the optical waveguide act as their own electrode. So again, it's a very efficient integration. So we're talking about 30 femtofarad, and we can really push the frequency limit to the terahertz regime. Also, what's important here is that we use the pockets effect because this is quasi-instantaneous, and other effects are also bandwidth limited. So eventually we are just limited by the electrode and the package design, but not by the modulator component itself. And this is a measurement up to 990 gigahertz, and you can see it's all flat. That said, this measurement has been taking a couple of years because you need to do the stitching. It's a lot of measurement setup, so it looks really easy, but it's quite complex to just measure this. And it's also energy efficient because it's just a lumped capacitive load for the driver. There's no 50 ohm termination, there's no traveling wave electrodes, so you can also apply the differential voltage. And this means you save a factor of 2 in terms of voltage. So normally, if you look at this right picture, you have a ground, signal, ground, but we can usually use the signal bar, signal, signal bar, which is coming out of the driver anyways. But normally we would just throw it away. Here we can use it. And eventually, you can even think of monolithic integration together with electronics on the same die. So that was a demonstration back in 2020 where we had electronic driver in BiCMOS silicon germanium, and directly at the output stage of the driver, we post-processed the plasmonic modulators. So very, very tiny integration, ultimate bandwidth density, if you want. And it's also scalable because it can be integrated on standard silicon photonics. So we work with IMEC here on their 200 millimeter platform. We use the standard platform, and then we post-process all the plasmonics part. And well, of course, if you look at plasmonic materials, I've shown you we use some special metals. Special means gold. It's not so special, actually, because any laser in this world uses gold. I think it's not so exotic. And also, it's added as a last step, so you can think of it as a redistribution layer. So to sum up, it's a technology which is highly scalable as it's integrated on standard silicon photonics. It's energy efficient because it's a capacitive load. It's terased fast, measured up to 900 gigahertz, and it's micrometer small in the 10 micrometer regime. So what can we do with it? A lot, but also IMDD and also CPO. And I mean, we have heard these things before. Just a quick recap. I stole this from NVIDIA website. It's not just about power reduction, which is of course very important, but also about reliability and resilience, which may be much better than pluggable receivers. The question is also, if we think about bandwidth density, how do we unlock the 400G per lane and beyond? How do we really get there? How do we bring all the components together? And in terms of modulators, our suggestion here is also to use resonant ring modulators, RMs. And the way we implement it is, again, we use standard silicon photonics for all the routing. Then we have a racetrack in silicon photonics, and then the active plasmonic phase shifter inserted in here. So the phase modulation changes the coupling condition and modulates the intensity of light. In the on state, the light largely just passes through, so we have a relatively low insertion loss of 1.2 dB, which was unthinkable a couple of years ago when the first modulators we did were like 40 dB of insertion loss. So this is a huge improvement, and we are quite proud of it. And also, because we have a very efficient phase modulation, we can have a design with a relatively low Q factor. So the electro-optic bandwidth is still really high with 170 gigahertz in this implementation. And another consideration with RMs is that typically they are not temperature stable. And with plasmonics, we have this section which is in the plasmonic regime, and then we have all the silicon. And interestingly, those two sections counteract each other. So you have one phase temperature shift in silicon and another one in the plasmonic section, and luckily it turns out to improve the resilience against self-heating. So in this graph, you see the silicon microring modulator, the reference, and then the improved temperature stability for the plasmonic. So this is showing a bit of the history. What can we do 400G per lane? So in 2023, we were not yet able of doing this. So we showed 100 gigabaud NRC at elevated temperature. So it was a really simple lab demonstration. We implemented a tech below the device and heated it up to 85 degrees, and we ran it for a couple of hours, monitoring the bit error rate, and it was running fine. But obviously we want more, we want higher speed. And then in 2024 was the first time when we actually could show the 400 gigabit per second, but it was still with a PAM8. So with a PAM4, which is a simpler modulation format, which would be what we prefer, we did not quite hit the 400G yet. This is also limited by the electronics that was available. And then last year, finally, we got better electronics, and we could do the 400G with PAM4 as well. And here the extinction ratio is still rather limited because the drive voltage coming out of the driver at such speed is relatively low, 700 millivolt. But I think there's lots of improvement on both sides, on the PIC side, but also on the electronic side. And I'm really looking forward to what's coming. And I think, yeah, these are also the next steps. I think co-design between the driver and the PIC. And of course, also we want to implement a next generation differential drive design. So that's it from my side. Thank you very much. And I hand over back to David.
Thank you, Claudia. So it's really exciting to see how far this technology has come. If I think back, I think 12, 13, 14 years ago, we were sitting in Zurich together and discussing about this, discussing how to measure the first generation. So it's really exciting to see how far this has come. And thank you for giving us this overview here in this session. We're going to move to our last speaker in this